Voy a apagar la luz detrás también. Un momento. Listo, ya estamos transmitiendo. Luan, por favor, puedes abrir el micrófono. Listo, ya estamos transmitiendo. Luan, por favor, puedes abrir el micrófono.
Okay.
Listo, ya estamos transmitiendo. Luan.
Okay, so it's my great pleasure to introduce our last speaker today, Professor Carlos Kenny. As usual, as is a tradition in ICMAM Latin America, just let me make a short introduction about Professor Kenny. Professor Carlos Kenny is an Argentinian mathematician. In the Department of Mathematics at the University of Chicago. Professor Carlos Kenny is an Argentinian mathematician.
Duan, disculpa un segundo, por favor. Duan. Duan.
Los participantes.
Un segundo, por favor. Duan, hay mucho retorno y creo que no se escucha muy bien. Hay mucho retorno y creo que no se escucha muy bien. Ok. No, disculpe, creo que tal vez es mejor hacer la presentación desde aquí para que no perdamos más tiempo.
¿Cómo no?
Disculpen por los problemas técnicos. Es
Sí,
que
sí, no hay ningún problema.
para que no perdamos más tiempo. Disculpen por los problemas técnicos.
Sí, no hay ningún problema.
Para que no perdamos más tiempo. Aló. Necesitamos que no haya retorno. Aló. ¿Hay retorno?
Parece que no.
Bueno. Okay, sorry for the delay. I am going to present now Professor Kenny. I think it's better for everyone to start now. I want to thank Professor Kenny for being here and for his patience. He has been very patient now, and I'm sorry for that. It's the first time we're in a hybrid format, so I hope you understand that this kind of issues can occur. But it is a great pleasure, and it is really a honor to have Professor Kenny here. He's going to talk about interior and boundary unit continuation. I hope everybody can enjoy and learn something from his talk. Welcome, Professor Kenny. Professor Kenny is a amazing mathematician, also famous mathematician, and he has supported our activities since 2022. So we are very thankful with him. Please, Professor, I hope you can feel welcome here, and please go ahead.
Okay. Thank you very much. First, I would like to thank you for the invitation to give a talk here, and also for putting together such an interesting program and for promoting mathematics in Latin America. Okay, so oops, something is happening here. Okay. So today we will be considering unique continuation for elliptic operators of the form L of u equals ddxi aijx ddxju plus bix dxiu plus c of xu equal to 0, where the coefficients aij are elliptic in a connected open set. And in the case when the coefficients aij, bi, and c are real analytic, then elliptic regularity shows that U is real analytic. And hence, if U of x0 is 0 of infinite order at some point x0, then U must be identically 0. If this property holds, we say that L has the strong unique continuation property. If L of U equals 0 in omega and U identically 0 in omega prime contained in omega with omega prime open implies that U is identically 0 in omega, we say that L has the unique continuation property. And if support of U is contained in a compact subset of omega, implies that U is identically 0, we say that L has the weak unique continuation property. Now, it turns out that because of work of Adamar on uniqueness in the nonlinear Cauchy problem, and because of the Holmgren uniqueness theorem from the beginning of the 20th century, it became clear that it would be desirable to establish the unique continuation property for operators whose coefficients are not necessarily real analytic or even C infinity. The first results in this direction were due to Thor Karleman in 1939, who considered an operator of the form the Laplacian plus a constant in 2 dimensions, and where not a constant, a variable coefficient C, which is takes the role of a potential, which is locally bounded, and he proved the strong unique continuation property for that. So this was the first result in this type of unique continuation. And he introduced a method, which is called the method of Karleman estimates, that has been a fundamental tool in the subject ever since. So to give you an idea of what a Karleman estimate looks like, I wrote down an inequality here where lambda to some power times e to the lambda phi f in L2 of some open set U is controlled by a constant times e to the lambda phi Laplacian of f in L2 of the same domain. And the big important fact is that you need the constant c to be independent of the parameter of lambda, which could be tending to infinity. And this is supposed to hold for suitable functions phi. And it turns out that such estimates easily imply the strong unique continuation property for the Laplacian plus C. Now, how Karleman got the idea of proving these estimates is beyond me. It's completely amazing. And this method has been extremely successful. And there's a huge literature on the application of Karleman estimates to uniqueness questions. You can read Hormander's books, and there's many, many instances of uses of Karleman estimates. Then I want to point out that Muller in 1954 extended Karleman's result to higher dimensions. Now, in the early 50s and in the late 50s and the early 60s, there were huge progress in the subject. People who made progress were, for instance, Cordes, Agmon, Arongine, Nirenberg, Calderon, Hormander, Treves, and many others. A result that I want to highlight here is from 1962, due to Arongine, And then two other Polish collaborators whose name I better not pronounce. And they use Karleman estimates to prove the strong unique continuation property for operators L of U, like I wrote at the very beginning, with the matrix AIJX elliptic, Lipschitz continuous, and the coefficients BI and C on the lower order terms merely bounded. Then, soon after, Pliss and Miller constructed examples of coefficients Aij of x, which are elliptic, and instead of being Lipschitz, are of class C alpha for any alpha less than 1, for which the unique continuation property fails. So the Lipschitz regularity is the borderline regularity here. And much long after, not so long ago, Filomov constructed examples of non-zero compactly supported solutions with coefficients ij elliptic and Helder continuous for any order strictly less than 1. It's interesting here that in 2 dimensions, all of these results are true with just bounded measurable coefficients. And here we see complex analysis playing a role. Another topic of interest in this area arising from mathematical physics is unique continuation at infinity. For example, in quantum physics, one considers Schrödinger operators of the form Laplacian plus C as a self-adjoint operator on L2 of Rn, and one wonders if such self-adjoint operators could have embedded eigenvalues. In this case, this means coefficient numbers lambda less than or equal to 0, such that there is a solution V to lambda plus C V equals lambda V with V in L2. And V, of course, not identically 0. So in 1929, von Neumann and Wigner constructed an example when n equals to 1 of such an object for a C tending to 0 as x tends to 0 at infinity. Relic in 1943 used Karleman estimates to show that this cannot happen if the potential C is bounded and of compact support. There have been, over the years, over the decades, hundreds and hundreds of results in this direction. I'll just give an example that I'm particularly fond of. In the case when n is bigger than or equal to 3, and we take potentials in the scale invariant class ln over 2, this cannot happen. And this is work that I did with David Jerrison in 1985, combined with work of Ionesco and Jerrison in 2002. As far as the case of n equals to 2, this fails. With Nadirashvili in 2002, we produced an example of a C in L1 of R2 for which there are embedded eigenvalues. And research on this direction is an ongoing project. A lot of people are working on this kind of issue. The unique continuation principle has found many applications to nonlinear PDE in various contexts. For example, there's a famous result on conditional regularity for the Navier-Stokes equations in R3 due to Escariaza, Seregin, and Zverak, who proved that if the L3 norm of the velocity remains bounded, then the solution exists forever and is regular. And this is the strongest conditional regularity result up to date, and it uses unique continuation for parabolic equations. In work that I did with Frank Merrill on the nonlinear wave equation, we proved that self-similar compact solutions for the energy critical wave equation don't exist using also unique continuation. The theory of unique continuation is also fundamental in control theory and in inverse problems. In inverse problems, the Karleman estimates are not used to proving uniqueness questions, but to produce certain classes of solutions that are then tested in the inverse problem to give results. In the late 1960s, besides the Carl-Lemon method, another method to study unique continuation emerged in a work of Agmon, which was inspired by the three-circle inequality in complex analysis using convexity of means. The method was further developed by Jerry Kasten and independently by Garofalo and Lin in the 1980s. This method ultimately relies on what we call doubling properties of solutions. This is the property that the doubling property is that the L2 norm of the function u, or u squared, integrated on the ball of radius 2r, is controlled by a constant that does not depend on r, but may depend on u and on x0, the L2 norm on the ball of radius r. And the fact that it's called a doubling property is because 2r is the double of r. Now, it is easy to see, it's a simple exercise, that if a function verifies the doubling property, it cannot vanish of infinite order at the point x0 without being identically zero. So that's the connection between doubling properties and unique continuation. And it turns out that doubling is closely tied to quantitative unique continuation. So the notion of quantitative unique continuation originates in a work of Donnelly and Charles Pfefferman from the late 1980s. This work was motivated by a geometric conjecture of S.T. Yao from 1981. Yao's conjecture is that if Mg is a compact Riemannian manifold, and we take a non-zero eigenfunction of the Laplace-Beltrami operator with eigenvalue delta, then for large lambda, when the eigenvalue is very large, the n-1 dimensional Hausdorff measure of the zero set of u, which is called the nodal set, and it's denoted by n of u, has to be of the size of the square root of the eigenvalue, lambda. This today is an open problem. The set u equals 0 is the nodal set, and Donnelly and Pfefferman in 1988 proved the conjecture of Yao in the case of M analytic for analytic manifolds. So the philosophy of Donnelly and Pfefferman was that an eigenfunction should behave like a polynomial of degree square root of lambda. Their work was divided into two parts. There were some local estimates and some global estimates. The local estimates held for smooth manifolds. But to pass from the local to the global, they needed to use analyticity. So for the local part, Donnelly and Pfefferman showed that eigenfunctions vanish of order at most, with eigenvalue lambda, vanish of order at most c times square root of lambda, in analogy with polynomials of degree square root of lambda. This followed from a sharp estimate on the doubling constant. They showed that for an eigenvalue of eigenvalue lambda, the doubling constant is 2 to the c square root of lambda. And this has the right implication on the vanishing order. And this was proved by Donnelly and Pfefferman using Carl-Lemon estimates. Now, not long after, a proof using the Garofalo-Lin method was given by Lin, Kukavitsi, and Manguvi, all three independent of each other. Let me illustrate the Garofalo-Lin method because it's a very instructive thing. So I'm going to do it in the simplest setting, where we have a harmonic function, Laplacian of u equal to 0, in an open set omega, and 0 belongs to omega. And let's pick a capital R so small that the ball of radius r around 0 is still in omega. And the radius r will be, capital R will be considered to be of the unit scale, and we will be considering small scales, 0 less than r less than capital R. So now I'm going to introduce three quantities. The first one is the integral, or the boundary of the ball of radius little r of u squared, surface integral. So that's the L2 norm on the surface of the ball. Then d of r is the Dirichlet integral, is the integral of the gradient squared inside the ball. And then n sub 0 of r is the ratio between r dr and h of r. So the 0 denotes the fact that the balls are centered at 0. And this quantity, n of n0 r, is a scale invariant quantity that's also invariant under multiplying the u by a constant. So this is a very nice quantity, and it's called the Holmgren frequency function. It was introduced by Holmgren in the late 1970s, and somehow Holmgren was able to see that this is, even though it's scale invariant, is a monotonic quantity in R. So n0 of r prime, no matter what harmonic function you put in there, will be bigger than or equal to 0. So let me show you how you deduce unique continuation from that. One can compute, just by using a Green's theorem and differentiation, that the log of h prime of r, where h of r is the L2 normal, L2 integral on the boundary of the ball, is 2 over r times n0 of r. So this is an equality. So if I integrate this equality between s and r, I get that the log of h of r minus the log of h of s is twice this integral of n0 of t dt. But now I know that n0 is increasing. So the worst value is taking at the unit scale n0 of r. So I pull that out, and I integrate dt over t, so I get the log of r over s. So suppose now I take s equal to r over 2. Then, and I exponentiate. Then I get that h of r is less than this quantity, which just depends on the frequency function at the unit scale, times h of r over 2. And this is doubling. Okay, this is doubling on spherical means, but then you can integrate on all the spheres between 0 and r0, and you get doubling for the solid integrals. And doubling rules vanishing order. So this is a very quick proof that harmonic functions cannot vanish of infinite order. But you have to see this fact. Once you know that it is true, of course, if you work hard enough, you can prove it. But knowing that it is true is a kind of an amazing insight. Another fact that is very important in geometric applications is that the only case for which n0 prime is identically 0, when is the frequency constant, is exactly when u is a homogeneous harmonic polynomial. And the constant has to do with the degree of the polynomial. So a related topic to the nodal set also of geometric interest is the size of the critical set. The critical set is the set of points where the gradient of the solution u is 0. And there's also the singular set, which is nothing more than the intersection of the critical set and the nodal set. That's the set where simultaneously the gradient and the function vanish for solutions. Now, geometers are interested in the sizes of these sets. So when you study this for solutions of L of u equal to 0, if L of u has analytic coefficients, you can use analytic theory to prove that the n minus 2 Hausdorff measures of these sets can be controlled. So it's one less than what you expect for the nodal set, one less dimension. For smooth coefficients, nobody knew how to do this for a very long time. And then towards the end of the 20th century, very inefficient estimates were available. Recently, there have been major breakthroughs in the study of the nodal set, the critical set, and the singular set. For Yao's conjecture on the nodal set, Logunov and Melinikova in 2016 made important progress that added to our toolbox to study unique continuation. And what Logunov proved in 2 papers in 2016 was that the nodal set in Hn-1 measure has a lower bound by C1 square root of lambda, as in Yao's conjecture, and has a polynomial upper bound, lambda to some constant. Now, before this work, the best upper bound that you had in the smooth category was double exponential in lambda. That was work of Hart and Simon. Anyway, after this breakthrough, for the corresponding question on C1 domains and Dirichlet eigenfunctions, Logunov, Nadirashvili, Nazarov, and Melynikova were able to establish both the lower upper bound and the lower bound of C square root of lambda in 2017. The new idea of Logunov and Melynikova was in the style of Calderon-Zygmunt theory. So, it's something that's very close to Charles Pfefferman, of course, also close to myself. And the idea involves a combinatorial and geometric argument. It was a stopping time argument in the spirit of the Calderon-Zygmunt decomposition, where you start with a cube and you start partitioning it into smaller and smaller subcubes according to some prescribed ingredient as to when you stop. And what Logunov and Melynikova showed was that as one subdivides a fixed cube into smaller and smaller subcubes, if you take a weight and you understand the doubling index, how much it can double, this drops for many subcubes. It gets closer and closer as if the weight were a constant. And this was the real key new ingredient for their proof. Okay, the second advance that I would like to discuss is also geometric and comes in the work of 3 geometers, Cheeger, Neighbor, and Valtorta, in the period 2013-2017, and this is in various combinations of these 3 authors. Remarkably, it also uses ideas from harmonic analysis and geometric measure theory. It culminates with works by these authors in works in geometric measure theory and regularity in geometric variational problems. And in fact, it was in this type of subject that Almgren discovered, working in this subject, that Almgren discovered the frequency function. And what he discovered is that it also holds for multiple valued harmonic functions, even in variable coefficient settings. And this was very important in his monumental regularity theory. This was over 1,000 pages. The new results of Cheeger, Neighbor, and Valtorta deal with effective bounds on the critical set and the singular set. So I will make a brief review. I'll make it extremely brief on what Hausdorff measure, Hausdorff's dimension, and Minkowski content, upper Minkowski content, and upper Minkowski dimension. So Hausdorff's measure is something that people study in graduate school, and so it's more familiar. You take covers by open sets, and you take the diameters to the power s, and you take smaller and smaller diameters, and you look at the sums, and you take the infimum. And the dimension, Hausdorff dimension of a set is the infimum of the s's for which the Hausdorff measure is 0 for s is for s bigger than 0 for s is smaller, I'm sorry. And then there's a more precise notion, which is this Minkowski upper dimension and upper content, where you take a tubular neighborhood of A and you take the volume of the tubular neighborhood and divide by the normalization of the right power of R and take the limit, the lim sup as R tends to 0. And that's the Minkowski content. And the Minkowski dimension is the infimum again, or supremum, just like the Hausdorff dimension. And it's easy to see that the Hausdorff dimension is majorized by the Minkowski content, and the Hausdorff measure and the Hausdorff dimension is the other way around with the Minkowski content. And it's important to know that the Hausdorff dimension bound has limited application, because if you look at the rationals in the real line, their dimension is 0. But their upper Minkowski content is plus infinity, because they're everywhere because they're dense, but their dimension is 0. So these new effective bounds are expressed in terms of the Minkowski content and in terms of the frequency function evaluated at 1 point for a unit scale. So let me give you what Neighbor and Valtorta proved in 2017. They proved that with just Lipschitz coefficients and bounded lower order terms, you have a good bound of the Minkowski content of the critical set and of the singular set. And they yield bounds of dimension n-2, which are effective. You can compute in terms of the coefficients and the frequency function at the unit scale. This method of proof used very sophisticated GMT, something called quantitative stratification, which they developed jointly with Cheeger, an expansion of solutions into homogeneous harmonic polynomials and strengthening of it. This was due to Qing Han in his thesis in 1994 under Fan Hua Lin. And another key ingredient were covering lemmas. This is again harmonic analysis, and the important ones were the reminiscent of Carlson's corona decomposition in harmonic analysis. Now, in the application of these ideas, there always had to be a combination with the existence of a single monotonic quantity like the frequency function. Okay, so I grew up by studying boundary value problems. So I always have the tendency of asking, what about the boundary? Can we say corresponding things not in the interior, but at the boundary? What's happening? So let me start with an old story. This is a simple question in complex analysis, let's say. Suppose I give myself a Lipschitz domain in R2 and a function u, which is harmonic in the domain, and it and its gradient are continuous up to the boundary. And suppose I have a set on the boundary which has positive length, h1 of E is positive, and we know that this harmonic function is 0 on E, and its normal derivative is 0 on E. Then this forces U to be identically 0 inside of E, of omega. And the reason is that you make the gradient of U into an analytic function by the Cauchy-Riemann equations, and you take the absolute value of that analytic function and its log, and then it would be a minus infinity on a set of positive measures on the boundary, and by subharmonicity of the log of an analytic function, this is impossible. So the only possibility is that the function is 0. The Lippmann-Burrs in the early 1940s asked if this fact extended to higher dimensions. And this was open for many, many years until Tom Wolfe and then Jean Bourgain and Tom Wolfe in a joint work were able to show that this is false. This was towards the beginning of the 1990s. They showed that there exists a harmonic function in the upper half plane, non-zero, which is of class C1 alpha up to the closure for some alpha less than 1, such that the set on the boundary, which is the Rn minus 1, where it has positive measure, where u and the normal derivative is 0. So this came as a shock to many of us, but there you are, right? Now it is interesting that here the problem of whether such a function, if instead of being just C1 alpha, it is C2 up to the closure, can be, has the same answer or not. And this is still an open problem. Now I want to, in the remainder of the talk, switch gears a little bit and bring up another problem related to Burr's problem, but that surprisingly arises in a very applied context in optimization and control theory. So we start out with a domain, a smooth domain in Rn, a harmonic function in the domain, and this function is between 0 and 1. Now we fix 2 points in the domain, which are different. One we call x0, the other one call x1. The problem coming from optimization is to minimize the value of u at x1 among all such harmonic functions u between 0 and 1, such that at x0 they take the value 1/2. Okay, so it's a simple problem. And this was proven by Schmidt, who is an expert in optimization, who proved that there exists a unique minimizer u tilde, and that this u tilde has what is called the bang-bang property. That means that u tilde takes only 2 values on the boundary. It's either 0 or 1. And in his proofs, he showed that this is equivalent to the following boundary unique continuation problem. Suppose that u is harmonic in omega, omega smooth, smooth in the omega closure. U is 0 on an open set on the boundary open set, and the set of points where u is 0 is positive, where the normal derivative of u is 0 has positive surface area. Then you want to prove that u is 0. And this was proved in an earlier work by Schmidt and Wick. And we can view this as sort of half of Burr's problem, because in Burr's problem, both u and du they knew have to be bounded on a set of positive measures. And I'm sorry, I need to take a break because somebody knocked at my door. 1 second.
No problem, Professor.
I apologize. They're offering me free roof inspection. Anyway, so this is halfway into the Burr's conjecture, because of course here we only assume that it's a set of positive measure in which this is 0, but here we're assuming that it vanishes on a whole open set that contains this. Now, from smooth domains, this was extended to C11 domains by Fan Lin in 1991. And what Lin did is he used a very careful reflection argument across the boundary that reduces matters to an interior unique continuation problem for an operator with Lipschitz coefficients. And in the work where he did this, Lin raised the question of extending this to the class of Lipschitz domains. And the other thing that Lin proved using some geometric measure theory, namely Federer's dimension reduction argument, he showed that the Hausdorff dimension of of this set was in fact n-2 in the C11 case. So the next progress in this intermediate burst conjecture was due to Adelson, Escariaza, and myself, who were able to prove the corresponding result for convex domains. And in this paper, we introduced a boundary version of the frequency function. This was followed by works by Adelson and Escariaza in 1997, and Kukavica and Nystrom in 1998, who proved the same result for domains that are C1 Dini. So a C1 Dini domain is a C1 domain such that the normal has a modulus of continuity that verifies the Dini condition that the integral of theta of S ds over S is convergent. And they also use frequency function methods. And Adelson and Escariaza also proved the same dimension estimate being less than or equal to n-2 for C1 Dini domains using the Federer reduction argument. But as I mentioned before, this is not an effective bound. Hausdorff dimension bounds are not effective. Now, again, after many years, in 2020, Xavi Tolsa was able to show that if we look at the singular set of the boundary, I mean, this is the control theory analog of the burst problem. For C1 domains or Lipschitz domains with small constant, the n-1 measure has to be 0. Otherwise, the function u has to be 0. And interestingly, the proof again was inspired by the ideas of Logunov and Malinikova, which are inspired somehow by the Calderon-Zygmunt decomposition. So an example by a student of Tolsa called Gallegos from 2023 shows that the n-1 Hausdorff measure is the optimal one you can use, even for Lipschitz domains with small constant or C1 domains. Okay. So I will now turn to a series of 3 papers that I wrote with my then postdoc Zihui Zhao, 2021, 22, 23, where we revisit the case of C1 domains, C1 Dini domains, inspired by the interior works of Neighbor Valtorta that I mentioned earlier. So the result is, let's take omega a C1 Dini domain. That means that the modulus of continuity of the normal is controlled by some function theta, which has this property. And assume we take 0 belonging to the boundary, and we take a non-zero harmonic function in the boundary, which is 0 on this open set of the boundary. We look at the singular set, which we now study up to the closure. So the set of X is in the closure of omega, for which u is 0, and the gradient of u is 0. Now we create something that I'm going to call under quotation marks the frequency function, because it is not a frequency function. It is a combination of 2 different frequency functions, one that comes from the interior and another one that comes from the boundary, and which somehow have to be matched at certain scales. And suppose that this object satisfies that it's controlled by the number capital lambda. Then the Hn-2 measure of the singular set is dominated, of course, by the Minkowski n-2 outer measure. And that's controlled just in terms of the Dini parameter and the frequency function. And in fact, this set is more than does measure being finite. It's what is called in GMT n-2 rectifier. Let me skip theorem 2, not to muddy the waters very much, and move to theorem 3, where it says that the C1 Dini assumption in this theorem 1 is absolutely sharp. What this means is that if you give me any modulus of continuity theta, so it's a function which is increasing, limit of theta of r at 0 is 0, but which is not Dini, so that means that this integral is infinite, there is a C1 domain in the plane whose normal has a modulus of continuity theta and a non-trivial, non-negative harmonic function in omega, 0 on an open boundary set, such that the n-2 measure of the singular set is infinite. So if you weaken the Dini condition, the n-2 bound fails. Now, it is also interesting that these constructions can be made to be convex. So it is good that in the convex case, we didn't do the dimension reduction argument. Okay. So since I think I still have a few minutes, I want to just give a little bit of an indication of how this is a proof that, before I do that, let me not forget to mention something else. This is an estimate on the singular set. I had mentioned the critical set before, which is the set where the gradient of u is 0 up to the closure, but where u is 0 on a portion of the boundary. Now, that is a much harder thing to prove, but recently, in joint work with Zihui, we managed to prove this, the same kind of estimate for the critical set, not on Dini domains, but on C1 alpha domains for any alpha. And of course, the case of proving that for the critical set for Dini domains is open, and it's a hard and interesting problem. So I'm just going to mention now, since I think we started late, so I can take a few extra minutes. Let me just say a few words about the proof of Neighbor and Valtorta on their results. But I'm not going to mention the proof of Neighbor and Valtorta because that's not what we use. We produced our own version of this. And it uses some covering lemmas of Neighbor and Valtorta in another work, in the regularity of geometric variational problems in the case of higher codimensions, which is the same topic that Almgren was studying in his discovery of the frequency function. So, and they were extending a classical work of Reifenberg from 1960 in geometric measure theory. So I'm just going to do this very briefly. So you take a Radon measure, and you then define what are the Peter-Jones L2 beta numbers from around 1990, which are a way to say that the support of the measure is well approximated by k-dimensional planes. Is what's encoded by these beta numbers. And Neighbor and Valtorta proved that if one considers a cover of something with a packing measure, one can estimate the mass of the packing measure in terms of the beta numbers by using a Carlson measure bound. And this is the key ingredient in Reifenberg's proof of I won't get into Reifenberg's work, but this was a version of what Reifenberg did, but it's much more quantitative. And this is the crucial tool in the application to the study of the singular set. Because what one can prove is an estimate of the beta numbers in terms of the drop of the frequency function, and by the monotonicity, this is a telescopic sum, and this allows you to add up this on different dyadic scales. So with that, I think I've said enough and I conclude. Thank you very much.
Thank you, Professor Kenny. Very interesting talk. I think we can try again if the sound from the auditorium is working now.
Yeah.
Because I think we have a question from there. Okay, we
Okay. Maybe, when you have a question. Can you hear me well?
Not exactly, but let's try.
Okay. No, my question is about the sharpness of the Dini condition in theorem 3.
Yes.
Maybe you can explain in which way is this condition sharp? I didn't understand well. Maybe if you can give more information about this.
Yes, I can. Thank you for asking me this, because it turns out that the idea for this construction goes back to a construction that I had in my thesis in 1977. So this is very close to my heart. So the idea is you construct these domains by constructing a conformal mapping from the upper half plane. And the function that you're going to use is going to be the Green's function, and the Green's function gets transformed by conformal mapping to the upper half plane, and there's a weight involved which has to do with the derivative of the conformal mapping. And it's in the construction of these special weights, which then give rise to conformal mappings, that you can see this Dini condition appearing. And the way it appears ultimately goes back to a very elementary and old fact in harmonic analysis, which is the following. We know that if you look at the Hilbert transform of a bounded function, this need not be bounded anymore. Okay, it's at most of bounded mean oscillation. On the other hand, if the bounded function has some continuity assumption, you may hope that the Hilbert transform is bounded. And the sharp condition for this is that the modulus of continuity be Dini. And it's exactly this that plays a role in the construction via the conformal mapping.
Thank you very much. Thank you very much.
Okay.
Okay, I think we have another question from the private chat. Say, Professor, is it possible to have a wiki regularity condition on the boundary and still compute the Hausdorff measure of the nodal set? For example, considering less regular boundaries than of C11 type?
Yes, I think that this is certainly something one can try to do. Nobody has done it, to my knowledge.
Okay, there's another question from the chat. Maybe I will encourage Mohamed, if you want to mute yourself, I can allow you, but you want, we can read your question. Let's see. Now, so in the chat, Professor, in page 20, the dimension, is it the classical one of a linear space?
Where do we, oh, have I just lost my page 20? Can you read what comes before, the sentence before? If not, I'll have to get back to my.
This is it's just in page 20. The dimension is the classical one, but
Yeah, no.
I don't know.
So no. It's the Hausdorff dimension or the Minkowski upper dimension that I define in the talk. In a transparency, I went over very fast. It's not the linear dimension. It's the Hausdorff dimension.
Okay, I think there is no more question. So, Professor Kenny, thank you again. Mohammed says thank you also
Okay.
for that interesting talk. Thank you for supporting our event again. I hope you have a good rest of the day.
Okay. Thank you.
Bye bye.
Bye bye.
For the participants, I will be sending an email confirming the Zoom link because we have lost the link we had. So tomorrow we will be beginning at 6 a.m. Colombian time. I think let me check the schedule. I think it's 1 or 2 p.m. in the Central European Summer Time. You can check in the schedule and just be checking your email because we will be sending the right links on. Thank you for being here. It is a pleasure always to have this participation from you. Bye bye.
Bye bye. Thank you.